All right, we've been working with exponential functions, but now we're going to talk about solving exponential equations. And to solve exponential equations, we have to know the one-to-one property. And it's actually a common sense property, but it does have a name. And I think some of your homework actually refers to it as the one-to-one property. Here's what it says. If b to the x sub 1 equals b to the x sub 2, if I know that is true, all right, then I also know, and it makes sense, that this is equal to this. Then x sub 1 must equal x sub 2. Whatever those exponents are up there, okay, if I have an equation and the bases are the same thing, okay, and that's the key. The bases have to be the same thing. If the bases are the same thing, then you can just drop that and set the exponents equal to each other. So, let's see how this is going to look. Get right to some examples. You're going to be asked to solve. And let's say that we have 5 to the x squared equals 625. Something like that. And we want to solve that exponential equation. It's actually not that hard if you have your root sheet handy, because what we want to do is we want to write this as 5 to the x squared. Hopefully we can write this side as 5 to a power. If you look on your root sheet, 5 to what power makes 625? Isn't it the fourth power? And once you've done that, then you can drop the 5's and just set the exponents equal to each other. X squared equals 4. Now, how would we solve that? Wouldn't we take the square root of both sides? Okay. I would take the square root of x squared and the square root of 4. So what would x equal? Positive or negative 2. Okay? And how could I check that? Couldn't I just put the number in? If I put a negative 2 in right here, if I put a negative 2 in, I'm going to square it, right? So negative 2 squared is positive 4. So this does check out okay. Let's do another one. That one wasn't that bad. Here, you try one. How about this one? 2 to the x minus 1 equals 32. I'll pause the video. You try that one. All right. I should have set 2 to the x minus 1 equal to 2 to the 5th, right? And once you've done that, then you can drop the 2's and you have x minus 1 equals 5. Add 1, don't skip steps. You'll make silly mistakes if you do. It's 6. So those first two are pretty easy. Let's look at another situation where maybe I have to do something a little different, like this one. Now, I can't write 32 as a power of 16, can I? No, no way. So what we're going to do is we're going to change both of these so that they have the same base. They are both a power of 2, aren't they? So this one is 2 to the 4th. 16 is 2 to the 4th, but the whole thing is to the x power. And 32 is 2 to the 5th. Now we're making progress. When I have a power to a power, that means multiply. So this is 2 to the 4x equals 2 to the 5th. And now we're ready to drop the 2's. So I have 4x equals 5. divide both sides by 4. So x equals 5/4. All right, so you're going to see something like that where you have to tweak both sides. Here's a good one. 1/3 to the x minus 1 equals 81. I told you that one of the things that we've got to be good at coming out of this year is exponents. This is a great example why. Okay, if you'll notice, I've got this thing in the denominator, which I need to be very careful with, all right? This 81, I can write it as a power of 3, can't I? Wouldn't it be 3 to the 4th? But if I'm going to be able to solve this, I've got to deal with this side, all right? This technically means 3 to the negative of x minus 1. All right, because a negative exponent means put it in the denominator. All right? So be cautious with that. You just need to, multiply it by negative. So what do I have now? I have the negative, or we could think negative 1 times x minus 1 equals 4. Distribute your negative through, you have negative x plus 1 equals 4, and then you just finish your algebra. Negative x equals 3, so x equals negative 3. All right, so you'll have some like that you'll have to deal with. Here's another type of problem you're going to have to deal with, the beloved fraction problem. Everybody's favorite. This one's actually not very hard. You just have to remember that if you square a fraction or if you cube a fraction, you do that to the top and the bottom. All right? So if you look at this side over here, can I write 27 125ths as a power of 3/5? I sure can. What's 3 cubed? 27. What's 5 cubed? 125. So we can write this side as 3/5 to the 3rd power, because when you cube, remember what cubing a fraction means. This technically means 3/5 times 3/5 times 3/5. And if I did that, I would get 27 over 125. All right? On this side, I still have my 3/5 to the x. And actually, this problem is done. Drop your 3/5, x equals 3. All right? Another fraction problem. How about 9/25 to the x equals 5/3? This problem challenges your knowledge or expertise of a negative exponent. Because in reality, if I want this to work, I need to write this side as 3/5 to the negative 1. Would you agree that 3/5 to the negative 1 is the same thing as this? Well, what is 3/5 to the negative 1? It's 1 over 3/5, right? And when you divide by a fraction, don't you multiply by the reciprocal? Right? So this is the same thing as 1 times 5/3. All right? So that's how that works. On the other side, I can write 9/25 as 3/5 squared, all to the x power. Don't leave out that x power. All right? And then we've got a power to a power right here. So I have 3/5 to the 2x equals 3/5 to the -1, and all of the hard part is over. Now I can drop the 3/5, and I have 2x equals -1. I can divide both sides by 2. X equals -1/2. All right? There's one other type of problem that I want to go over, and it's this idea of compound interest. Now, there are several compound interest formulas. This is a very basic one. Okay? So, the first formula is for n compoundings per year. Now, what do we mean by compounding the interest? Does anybody know? Interest is something the bank pays you for putting your money in the bank. It's not very much, okay? But they give you a little small amount of money for storing your money at their bank. Why? Because they're going to loan your money to somebody else. That's why. Okay, so they give you a little bit of interest, and when they actually add that money in, that's called compounding the interest. Okay, so it's actually added into your account. So for n compoundings a year, we have this formula. A equals P times 1 plus R over N to the NT power. All right? So what do all those letters mean? P is the principal. We're not talking about the high school principal. We're talking about the amount of money that you put into the account. Okay, how much money did you put into your savings account? R is the rate. Okay, the interest rate. N is the number of compoundings per year. And of course, it makes sense then that T is the time. Okay, and we're going to do an example with this. Let's say, for example, that $9,000 is invested at an annual percentage rate. You've heard APR before. That's what that means. Annual percentage rate of 8.5%. And it is compounded annually. Find the balance after 3 years. Okay, so we're going to use this formula up here. What am I going to plug in for P? 9,000. Let's go ahead and do that. I'm kind of short on room down here. So I'm going to have A equals 9,000 times 1 plus, what's the interest rate? 8.5%. Do we ever use 8.5 in a math calculation? Don't we always move it 2 places to the left first? So this is 0.085 up here, all over the number of compoundings per year. Isn't there just one? It's only compounded annually. It's compounded annually. So this is going to be a 1. All to the power that has the number of compoundings per year. This is the same n as this is. Okay? As 1 times how many years? 3. Okay? So from there on out, it's a calculator problem. All right? So you're going to have 9,000 times 1.085 to the third power. So it's just a calculator problem. All right? So if you use your calculator, 1.085 to the third times 9,000. And you get $11,495.60. Boy, I wish there was an account that you could do that with at the bank, but there's not. Most of the time, about the best you can do is a CD, a certificate of deposit, and you might get 2%. 2% per year. And you can't take the money out. Usually a CD is you're limited on, you have to keep it in the bank for a certain amount of time. If you keep it in for 3 years, you get a better interest rate than if you only keep it in for 6 months. So that changes. All right, let's do another. Let's actually look. This is our first formula. Let's look at our second formula. For what's called continuous compounding. That means the interest is compounded continuously. Now that doesn't mean it's going to be worth more, okay, because it's calculated more often. The formula is A equals P times E to the RT. Remember that little number E? I know it sounds strange calling E a number, but it is. Okay, in the math world, it's a number. So let's do one more example now, and we're actually going to do 2 problems in this. $12,000 is invested. Okay, $12,000 invested. The APR is 9%. Wouldn't that be nice? By the way, you can earn 9%. You can earn 12%, you can earn 18%, but to do that you have to invest normally in mutual funds. That's kind of a fancy way of saying it's not the stock market truly. Mutual funds are diversified through a bunch of companies instead of one company. If you're playing the stock market, you're investing in one company. If you're in mutual funds, you're investing in 20, maybe 30 companies, okay, at a time. So, but you can earn much better than 9% using mutual funds. That's probably a discussion for another day. And let's find the balance. After 5 years, if it is compounded A, quarterly, and B, continuously. Okay? Well, if it's compounded quarterly, we're going to still use our first formula. We're still going to use A equals P times 1 plus R over N to the NT power. But now it's compounded quarterly, which is why I wanted to do this one. It's a little bit different. The principal is $12,000, so $12,000 goes in for P. Then I have 1 plus the interest rate, 0.09, divided by the number of compoundings per year. If it's compounded quarterly, how many times? 4. So I'm going to put a 4 here. And then I'm going to have a 4 times 5 power. Now let's notice what happened to our formula here. What's a little different? Didn't I divide the interest rate by 4 this time? So it's going to make it a little bit smaller, right? It's going to make the interest rate smaller. You might think, well, if it's compounded quarterly, it's going to be worth a lot more. Not necessarily, okay? Because you have to divide the interest rate by 4. So from here on out, it's a calculator problem, all right? 0.09 divided by 4, and then you add 1 to that, and you get 1.0225 in here. 1.0225 to the 20th power. So I'm going to raise my answer to the 20th power. I'm just using an old calculator here to do this. And you get 1.56 times 12,000. And it is now worth $18,726.11. Okay, like I said, you're not going to find an interest rate like that in a savings account or a CD at the bank, but maybe in mutual funds you could. Now, if it's compounded continuously, it's actually an easier formula. It's A equals P times E to the RT. All right, it's a little bit easier formula. So my principal is still 12,000 times E to the power of 0.09 times 5. Okay? So what is 0.09 times 5? It's 0.45. Okay, this is 0.45. So then on your calculator, you have to do the E function, which is the second ln, to the 0.45 power, 1.568 times 12,000. So times 12,000, still 18,000 in some. $18,819.75 after we round it. Okay, so it's not that much different compounding it continuously. And we're going to stop there for today.